Have you ever tried measuring the thickness of a strand of hair or the distance between two planets? In chemistry and physics, the quantities we measure can span from unimaginably tiny to incredibly vast, and for all of them, we need consistent, reliable units. That's where the SI unit of length, the meter, comes into play. Originally, back in 1889, the meter was defined as the distance between two scratches on a platinum iridium bar stored under carefully controlled conditions. But as science advanced, we needed more precision. In 1960, the definition was refined using the wavelength of krypton 86 radiation. And finally, in 1983, we arrived at today's ultra precise definition. 1 meter is the distance that light travels in vacuum in 1 divided by 299,792,458 seconds. Yes, that exact. This makes the meter not just a tape measure standard, but a truly universal constant based on the speed of light itself. But what happens when a meter is just too big? That's often the case in chemistry, where we deal with molecules, wavelengths, and particles on a microscopic scale. So we use submultiples of the meter. A centimeter is 1/100th of a meter, that's 0.01 meter. A millimeter is 1,000th, written as 10 raised to the power minus 3 meters. Then we go smaller. The micrometer, also called the micron, is 1/1,000,000th of a meter, 10 to the power minus 6 meters. Still too large? We go even tinier, the nanometer, 1/1,000,000th of a meter, or 10 raised to the power minus 9 meters. These units help us measure wavelengths of light, diameters of cells, and even the spacing between atomic layers in crystals. It's like having the perfect set of zoom lenses for every scale in chemistry. Now let's switch to the other extreme. What if a meter is too small? For measuring distances across cities, countries, or even space, we need larger units. Enter the kilometer. 1 kilometer is equal to 1,000 meters, written as 10 to the power 3 meters. This multiple is widely used for measuring roads, flight paths, and even distances between planets. It's much more practical than saying 1 million meters. Just like we zoom in with microns and nanometers, we zoom out with kilometers. These multiples make scientific communication smooth and scalable, whether you're studying the molecular scale or mapping Martian landscapes. On screen, you see a scale showing how meters transition into kilometers, giving you a sense of just how far we can stretch our unit system. When it comes to the cosmos, even kilometers aren't enough. Imagine trying to describe the distance from the Earth to the Sun in meters. You'd be dealing with numbers containing 11 zeros. That's where non-SI astronomical units come in. The first is the astronomical unit, or AU, defined as the average distance from Earth to the Sun, approximately 1.496 times 10 to the power 11 meters. Then there's the light year, which is the distance light travels in 1 year. That's roughly 9.46 times 10 to the power 15 meters. And for even larger scales, we use the parsec, which is about 3.08 times 10 to the power 16 meters. The parsec is defined based on the angle subtended by one astronomical unit from a distant point in space, a clever application of geometry in astronomy. These giant units help us express cosmic distances in manageable numbers, essential in astrophysics, astronomy, and space chemistry. Now, let's shrink back down. We're beyond the nanometer scale. Some chemical phenomena happen at such tiny scales that even nanometers feel too bulky. That's when we turn to the angstrom, which equals 10 raised to the power minus 10 meters. The angstrom was historically used to express bond lengths, atomic radii, and wavelengths of visible light. For instance, the average covalent bond length between hydrogen and chlorine atoms is around 1.28 angstroms. but modern science prefers the nanometer for SI consistency. And if you want to go even smaller, into the realm of nuclear physics, there's the Fermi, named after physicist Enrico Fermi. 1 Fermi equals 10 raised to the power minus 15 meters and is used to measure the size of atomic nuclei. These ultra small units allow us to explore dimensions far beyond the visible, where electrons orbit, nuclei split, and quantum magic happens. Let's take a moment to compare the vast range of length units we've talked about, from the unimaginably small to the astronomically huge. Starting on the microscale, we have the centimeter, 10 to the power minus 2 meters. Then millimeter, micrometer, nanometer, angstrom, and finally Fermi, each smaller than the last by powers of 10. Now zooming out, we go from meter to kilometer, then to astronomical unit, light year, and parsec, each one progressively larger by factors of thousands or millions. On your screen, you'll see a visual bar that compresses this entire spectrum into a single glance, showing just how flexible and far-reaching our measurement system truly is. From atoms to galaxies, one unit system connects it all. So why does all of this matter? Why should a chemist care about light years or Fermis? The answer is simple. The choice of unit defines the accuracy and relevance of our measurements. In chemistry, choosing the correct unit allows us to clearly express bond lengths, molecular sizes, and reaction scales without confusion. Measuring an atomic radius in meters would result in an inconvenient decimal mess, but nanometers or angstroms fit perfectly. Similarly, astronomers need parsecs and light years to track galaxies and nebulae. The SI system, along with its derived and non-SI units, provides a versatile framework that scales seamlessly from the quantum to the cosmic. So, whether you're analyzing X ray wavelengths or calculating interstellar travel paths, you're using the same language, just in different dialects. I hope this session helped you appreciate the importance of length units in science. In our next topic, we'll explore time and mass units, how they work together in formulas, and how they govern every physical and chemical process. Until then, keep measuring, keep wondering, and remember, in chemistry, even the smallest length makes the biggest difference.